Okay, so what we would like to do now is think about how calculus can help us analyze some polar curves. So let's start with something that you may know. That is that if you want to find the area of a circle, you simply multiply pi by the radius squared. Yay! So that is how you find the area of a circle. We know that. But let's suppose you want the area of just one slice of the circle. Okay? That slice. Let's call this some angle theta. Well, this is not so hard to think about because really this is a proportion. It's a portion of the circle. And so if we took our total area, which is pi r squared, and we said, you know what, let's multiply just by a fraction that we want. Well, we only want theta divided by 2 pi of the circle, right? 2 pi is the whole thing, but if we just want a little piece here, we'd multiply by theta over 2 pi. Well, the pi's divide, and so you actually get that 1/2 times theta times r squared, remembering that theta is measured in radians, of course. Please, yes. Then the area of a sector of a circle is just 1/2 theta r squared. Okay, don't believe me? You probably do, but what if you want 1/4 of the circle? Well, what's the angle there? It's pi halves. So then the area should be pi halves divided by 2 pi times, let's say the radius is 3, times 9, which is r squared, times pi. Right? And right, because that's theta over 2 pi times pi r squared. So that should just simply be gone, pi fourths times 9, or 9 pi over 4. But of course that makes sense because it's 1/4 of the circle, and so if you did pi r squared and divided by 4, you would get 9 pi fourths. So the important thing is that the area of a sector of a circle is 1/2 theta r squared. Believe it or not. So how do we use that now to talk about the area of polar curves? So let's suppose, let's see, if we look back at what we did last time, that we had the limacon, whatever, or cardioid, rather, that looked like this. Okay, we had one that started at 1, 2, 3, 4, 5, came down to 3 by the time we got here, came down to 1 by the time we got here, and then 3 again, and then back. So it looked like this, right? So say we want to find this area. What is the area inside this cardioid? By the way, this is the polar function. R equals 3 plus 2 cosine theta, which we graphed before. So it looks like this. Well, thinking about it, let us think about one little sector of this cardioid. So let's say that we've got some angle here, d theta, a little change in theta. We can make it delta theta. It's an actual change in theta. And we've got a radius here, r, which is given by that, 3 plus 2 cosine theta. Now, if we were just to say, all right, the area of this little piece here is 1/2 r squared times delta theta, which is, by the way, 1/2 times r squared, which is 3 plus 2 cosine theta, all squared times delta theta. That is not quite correct, because what that is actually giving me, if I use the top piece, is that. It's giving me the sector of a circle. And if I use the bottom piece, it's giving me this. it's giving me the sector of the circle, right? So it's actually not giving me the actual area of this little slice with the cardioid. It's giving me a circular approximation where 1 is an under approximation and 1 is an over approximation. Well, oh my goodness, I mean, you can see where we're going, right? We're going to, well, what happens when you make that delta theta smaller and smaller and smaller and approach 0? Then your under approximation is going to get really close to the actual thing, and your over approximation is going to get really close to the thing, and really, 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 really close, so that we can basically say they are the same thing. In fact, we can't say they are the same thing. So imagine what we really want to do is similar to Cartesian, where we took rectangles to approximate the curve. We want to take sectors to approximate the volume. And we want to add up all these little sectors, right, from, in this case, 0 to 2 pi, in order to find our area. So what should that look like? Well, that should look like the integral from 0 to 2 pi of 1/2 times the r squared, in this case 3 plus 2 cosine theta all squared d theta, right? So d theta is like delta theta, but going to 0, getting super, super small. So basically, these are all our little sectors, and we're going to add them up from 0 to 2 pi. So in general, what we want is 1/2 times the integral from alpha to beta of r squared d theta. So it's a pretty straightforward formula. This is giving us the area of a polar curve enclosed by a polar curve between alpha and beta. Pretty straightforward. The hard thing is knowing where alpha and beta are to figure out where your bounds are, and it can get pretty complicated if you're trying to find the area, say, between two polar curves, and you need to find their intersection. But that's sort of the general formula for this area of a curve. Okay, so that's sort of area, and we can come back to that. But let us also think about a couple other things. So a reminder that for parametric equations, we had if basically x equals f of t and y equals g of t, then we knew that dy dx was given by dy dt divided by dx dt, right? We also found that the distance traveled was the integral from a to b, integrating the speed, which was dx dt all squared, plus dy dt all squared dt, right? So this was the length of the curve, which was also the distance traveled, and this was our slope. So there are a few things we knew. We also knew that the concavity of the curve was given by the derivative with respect to time of dy dx all divided by dx dt. So these are some things that we know from parametric equations, and so we want to now basically extend those to polar equations, because polar equations are really parametric equations. They can be written parametrically. So let's think about this. For polar equations, we know, you may recall that the x value is given by r cosine theta, and the y value is given by r sine theta. That's how you convert between polar and Cartesian coordinates. And that makes sense, right? Because if your radius here is r, then this value right here is r times sine theta, and this value right here is r times cosine of theta. So that's where that's coming from. Okay, but usually we're given r as some function of theta, which means x is actually f of theta times cosine theta, and y is actually f of theta times sine theta. So what that actually gives us is parametric equations of theta, where these were parametric equations of t, now it's in terms of theta. So that means that our position depends on theta, our x position depends on theta, our y position depends on theta, and so all of this stuff applies. So basically we know now that if we want to find the slope of a polar curve, that should just be dy d theta divided by dx d theta, which can get pretty nasty, right? Because this looks like a product rule issue here. We know that the concavity of a polar curve would be the derivative with respect to theta of that answer there, dy dx divided by dx d theta. We know that the length of a polar curve is the integral from alpha to beta of the square root of dx d theta all squared plus dy d theta all squared d theta. And so the same things apply to a polar curve as they do to a parametric curve. So this gives us the arc length, or if we're talking about something moving around, it gives us the distance traveled. So with this plus area, and remember area was 1/2 times the integral from alpha to beta of r squared d theta. These are sort of the main formulas we need to be able to analyze polar curves. So in the next video, we'll look at an example of analyzing a polar curve. Hooray!